Let's work our way through Activity 9. So on Activity 9, we're interested in building models to predict a numerical response. And the data set we're going to use is the offense data in Reg class, which contains some statistics about NFL teams over the course of about 10 seasons. And we would like to predict how many wins per season each team is making based on some of the statistics that were recorded about their performance. So step zero really in any sort of data mining project is to really figure out, okay, well, what should I really be predicting? I just said we want to develop a model to predict wins, but when we're dealing with a numerical response, we want to make sure that the shape of the distribution of our y variable is something that the data mining algorithms are set up for. So let's go ahead and load in the library reg class and the data that we're going to be looking at, and let's make a histogram of our win variable to make sure it's something that we can deal with. All right, now most data mining algorithms that are out there would prefer if the distribution of the variable you're trying to predict looks more or less like this. It's nice and symmetric. It's not too skewed off towards the right with outliers or anything. This is kind of the playground that the data mining models like to be in. So we're pretty good here. What happens if we don't see a shape like this? Well, very often we'll transform our y variable by taking the logarithm, taking the square root, etc. But there's nothing to really worry about here. This looks like the data mining algorithms are going to be happy with this distribution. All right, well, the first data mining model that was really invented was just multiple linear regression. So let's fit a model just predicting wins from the number of fumbles and the number of first downs over the course of the season. All right, so how do we fit a linear regression model? Well, the command is lm, and what we do is we set up the formula just like all the formulas that we've been constructing so far. We put the name of our y variable win, we put the twiddle, and then we put our predictor variables separated by plus signs. So fumbles plus first downs, and then we say where this data lives. This is in the offense data frame. And so we can fit that model, making sure our names are spelled correctly. And then we can look at the coefficients. One of the really nice things about the linear regression model is that we can actually talk about how the model is kind of approaching the relationship between the y variable and the x variables. So what we want to do is look at the coefficients of the fumbles lost here. And it looks like I didn't quite have that named correctly, but what we really want is just fumbles. And interpret what its value is. All right, so how do we do this? Well, we interpret the coefficient by first identifying what that value is. I'm going to just copy and paste that here. And then what we say is that two otherwise identical individuals who differ in x by 1 unit are expected to differ in y by, I'll just put in quotes, the coefficient units. And I'm going to fill in the pieces here so that we can actually put some meaning behind this interpretation. So when we're comparing two otherwise identical individuals, what are we really comparing? Well, we're comparing teams for the course of the year here. So what I'm basically going to say is we're having two otherwise identical teams who differ in x, which is the number of fumbles here, differ in the number of fumbles by 1 unit. Well, what are the units of fumbles? It's just a count, so I can just say by 1. Well, they're expected to differ in y. What's our y variable? That's wins. By how many units? Well, about minus 0.1 here. I'm going to round just to minus 0.1. And the units of wins, well, that's just a count, so I can just leave it as 0.1 here. Now, one more bit of the interpretation, because this is negative, I need to follow that up and say that the team with the larger value of x is expected to have the smaller value of y. So the team with the larger number of fumbles is expected to have the smaller number of wins. So basically it looks like the way the relationship is working in this data set, at least just predicting wins from these two predictors, is that the more fumbles the team makes, well, the smaller the expected number of wins are. Now, I do want to improve on this definition quite a bit because when I do say otherwise identical teams, that's kind of vague. What do I mean by otherwise identical? Well, we always interpret that with respect to the other predictors in the model. And in this case, we just have one. So what we would say is that two teams with the same number of first downs for the season, that's what I mean by otherwise identical. Two teams that have the same value for this other predictor variable, so two teams with the same number for first downs, but who differ in the number of fumbles by 1, they're expected to differ in the number of wins by 0.1. More fumbles, fewer wins. All right, so now we want to turn our attention to trying to build a predictive model. So we have the answers for our data right here. We'd like to develop a model that's going to be predicting well on new individuals that the model hasn't seen before. Now, when we do this, we need to figure out what should we be really using as our predictor variables. Very often, the data mining algorithms work better if the distribution of the predictor variables are also nice and symmetric, kind of looking like this. Now, we're going to forego looking at the histograms of all the predictor variables. They actually do look pretty good. All the predictor variables in this case are pretty symmetric, so let's just skip that and just dive right in. So, all right, if we're going to build a predictive model, we need to split our data into a training sample and a holdout sample, and we'll save that holdout sample to the very end after we're done picking our final model or tuning our model just to make sure that it's generalizing about as well as we expected it to. So in all other cases, we've always done the split by just random assignment, randomly picking rows to go in the training and the holdout. We're not going to do that here because this data has a special form. Namely, the first 32 rows are from 2002, the second 32 rows are from 2003. So why don't we go ahead and actually have as our training data the first few seasons up on record, and our holdout will be the last few seasons. So what I'm going to do actually is just define train rows, which we've always done before. Before we did, sample, and we did picking numbers at random here. But in this case, I want my train rows to just be 1 to 288. Basically the first 10 or so seasons of this, maybe 9 or 10 seasons. And when I go and put those rows in the train, I'm just going to use the same syntax that I always have. Let's put into train those rows, and then in the holdout, we're going to do everything but those rows. No need to do set C. There's no randomness here. We're simply selecting the first set of rows to go into the training. All right, so let's define those. And let's try to search for an intelligent regression model. So we have 9 predictors of the number of wins, and it may be the case that all 9 matter. It may be the case that only a few of them do. We'd like to eliminate the variables that don't matter, because that's actually going to increase our predictive accuracy. Our model's not going to be overfit, and so we need to do some sort of variable selection. Now, we're going to use the RFE command, recursive feature elimination, from the carrot package to help us to figure out what a reasonable looking regression model that should generalize well to new individuals should be. So the first thing that we need to do is to tell RFE how to estimate the generalization errors of the models that it's going to be trying out. We need to set up RFE control. Now here's where I'm going to rely very heavily on the corresponding file that's up on Blackboard, the numerical predictions.r file, because it has examples of how to run all of these models. So here's how to set up RFE control. I'm going to copy and paste that into here. We're basically going to say, all right, we're going to be doing linear regression, LM here. We're going to do repeated k-fold cross-validation with 5 repeats. By default, it's going to do 5-fold cross-validation as well. So we're defining an object called control, CRTL, that'll tell it how to estimate the generalization error. What else do we need to tell RFE? Well, we need to tell RFE what kind of models to be looking at. Do we want to consider all models with 1 predictor, all models that have 2 predictors, 5 predictors? What exactly do we want to be looking at? We need to define a vector called subsets that tells us how many variables we want to consider when building models. Now, in this case, and it's a fairly small problem, I'm just going to define this to be the numbers 1, 2, 3, 4, up to 9. Basically, let's consider every model that we can construct, excluding any interactions, just predicting from the variables themselves. All right, so if I define subsets to be 1 through 9, it'll go through all models with 1 predictor, all models with 8 predictors, etc., estimate the generalization errors for all of them, and it'll report back what seems to be a reasonable model. All right, so it's time to run RFE because it's going to be estimating that generalization error with repeated k-fold cross-validation, which is a random procedure. Setting the seed ensures we'll all get the same results. I'm going to go and kind of copy and paste some of this stuff that tells us how to actually do RFE here. And we need some data processing actually to get the training set into the right form. So specifically what RFE wants is a matrix or a data frame that just contains predictor variables and then a separate vector that has what the answers were, what the y variables were. So what I'm going to do is I'm going to copy my train data into a new version called train.reg for regression. Because I'm going to be modifying what this data frame is, and I don't really want to destroy what my original training data set is. I want to be able to go back to that at any point. All right, so I'm going to define a vector called y.train to be what the y variable is in the train.ref data frame. So this is just win. Oops, there we go. Oops, I was using RFE here. So let me change that to REG. All right, so y.train are the answers on the training set. And then what I need to do is to take out that column because we just want a data frame of predictors. So we'll take that out. We'll see that it disappears. All 9 variables here are just the predictor variables. All right, so we've already defined subsets. We're ready to set the seed, and we're ready to run RFE. Now, because I've named my training data frame train.reg, I want to make sure that's consistent. Y.train is something I've defined, subsets I've defined, and the control I've defined as well. So we'll run RFE, and this takes a while. It's fitting a lot of different models. And once it's completed, we can look at the output just by printing the contents of models to the screen, and it'll give us a bit of a narration for how different models did. All right, so expanding this, what we see is that, all right, of all the models that it considered, the best one with one variable looks like it had an RMSE that's estimated for its generalization error to be about 2.6 wins. We see as we increase the number of variables that are going into this model, it looks like we get pretty much just a uniform decrease in the expected generalization error. And in fact, the variable that had all of the predictors in it looks like it's going to be the one that's generalizing the best. Now, you will notice that the standard deviation of these estimates of the generalization error is pretty large. These are all, or a lot of them are within one standard deviation of the smallest value. If I were to go 0.2575 above, let's just do that, 0.2575, any model that beats this number would be acceptable according to the one standard deviation rule. So basically any of these models are okay with 5 or even more predictors, but let's go ahead and actually just fit the model that has all 9 of those predictor variables, because that had the lowest estimated generalization error. All right, so we're going to fit the model predicting win from all predictors on train and then see how well that it does. All right, so once again, I'll be using the LM command for linear regression, predicting win twiddle dot here because it's all variables here. I don't need to name them out and separate them by plus signs. We're going to be fitting it on the training data equals train, not train.reg, because remember that's just the data frame of all predictors. We can go back to our original training set. And then what we can do is run generalization error from reg class to figure out, all right, well, what is the typical size of the error this model makes on the holdout sample? And the answer is here for us. We see that the expected error here, or the measured error on the holdout, is about 2.37 wins. So our model looks like it can narrow down what the number of wins of a team is based on these 9 predictors down to maybe 2 or 3 or so. All right, well, we've talked about regularization and why that's a smart thing to apply to models. Basically, it allows the form of the model, how the model is being estimated, to both take into account the resulting model's bias and also its variance. So the bias is just the error that's introduced by using a model to approximate reality. More complicated models are going to have a smaller bias because they have kind of more wiggle room to give a reasonable reflection of reality. But very often, models with a low bias are very sensitive to the particular set of individuals that it was trained on. So we say that it has a high variance because the form of the model might look really quite different if we were to train it using a different set of individuals. And the generalization error model is tied into its bias and its variance. We need to find a good compromise of both. So the lasso procedure is able to estimate the regression coefficients not only just by minimizing the bias, but also taking into account the resulting model's generalizability. It gives it a penalty based on the size of the coefficients. It tries to shrink the coefficients as small as possible, as close to zero as possible, because coefficients that are zero indicate that there's no contribution from that variable, meaning that for all intents and purposes, we have a simpler model. That variable is not even really in it. All right, but it takes a lot of processing. So what we're going to do is to copy the original training data, or the original data set offense into offense.lasso. Because when we do processing, we need to make sure that we do this to both the training and the holdout sample simultaneously, and there's a lot of processing to do. All right, so I make a copy called offense.lasso. What I'm going to do is save the win column to just a vector y here. So that y is a vector of all the answers. And then what we're going to do is take out the win column from the offense.lasso. Just like RFE, basically the lasso wants just a matrix, just a data frame of predictor variables. All right, so that's step number one. Let's just make a matrix of all predictor variables and a separate vector containing the answers. All right, another thing that the lasso wants is to have every variable on the same scale, meaning that they all have the same average and they all have the same standard deviation. That way the size of the coefficient is indicative of how important that variable is. If we don't do the scaling, the size is tied into the units that the variables were measured in, and they're not necessarily that informative. So what we're going to do is to redefine offense lasso as the result of running scale on the data frame. Now note that converts it into a matrix, so we can no longer refer to columns with the $sign, but that's going to be fine. That's not going to really complicate stuff. So offense lasso now is just a matrix. All of the variables, all the columns have a mean of 0, standard deviation of 1. And now we're going to go ahead and split that, now that our processing is done, into the training sample and into the holdout sample. Now, we didn't do a random split in this case, so we're just going to do the same thing that we did before, where we have the first 288 rows be the training sample and the remaining be the holdout sample. And I already defined a vector called train rows, and I can feel free to just reuse that again. All right, so train lasso and holdout lasso are all set up. Almost there. Now what I need to make sure to have are the vectors containing the answers on both the training and the holdout. So I have my y vector, which has all of the answers in it, and so I want to define a vector train y and a vector holdout y that had the answers on the training and holdout samples in particular. So that's going to be some elements of my y vector here. I can simply just say which ones they are by referencing train rows, because that was telling me which elements, which rows were essentially going into the training data, and I can do minus train rows for the holdout. All right, now one thing about train.y and holdout.y is that these numbers are just the raw numbers. They're not scaled. When we do the lasso, we also want to make sure that we scale the predictor variable, the y variable as well. So what we're going to do is to create some additional variables here. We're going to define a variable, mean y, to be the average value of our y variable on the training. We're going to define SDY to be the standard deviation of our variable on the training set. And we're going to go ahead and scale the answers for the training set. How do we do that? Well, we take the values, we subtract off what the average is, which was mean.y, we saved it there. And then we take that result and divide by the standard deviation. And so this, well, I gotta run this as a chunk. And so this way, now when I look, I see positives and negatives. I can see that the average value of train y in this case is 0, and the standard deviation is indeed 1. All right, now what we need to do is figure out the appropriate penalty to be imposing on the sizes of the coefficients, this optimal value of lambda. All right, so how do we run this? Well, this is where I go back to my notes here, and I'm going to copy and paste some stuff up. All right. So we have library glmnet. Since we're going to be finding this optimal value of lambda with repeated k-fold cross-validation, it's important to set the random number seed so we all get the same results. And then run these two lines as a pair here. We're going to use cv.glmnet. Here's our data frame of just the predictors with scaled to mean of 0, standard deviation of 1. Our vector containing all the answers, scaled to have a mean of 0, standard deviation of 1. Alpha equals 1 because we're doing lasso. And then n-folds equals 10, basically saying, all right, estimate that generalization error with 10-fold cross-validation. So we can run these lines. It's tuned it, and we can look at the results. All right, in this case, it looks like the second to the smallest value of lambda had the lowest estimated generalization error. Here's the one that was suggested by the one standard deviation rule. We can get out what those two values are just by printing the results to the screen here. And what we're going to do is to now just go ahead and use a value of lambda that's pretty close to this and actually fit the model. So I'm actually done with this part, so I'm going to cut that and paste it down here. All right, so now we're actually going to fit the lasso with this particular value of lambda. And we're going to left arrow that to the result into an object called lasso. So how do we do this? Well, we can define a variable called lambda grid, which tells us the value of lambda that we want to be fitting. And this can be a vector in case I want to be fitting multiple lambdas at once. In this case, I just want it to be 0.002, so I'll leave it at that. So to fit the lasso regression, the command is glmnet. Here's our data frame of the predictor variables that have been scaled. Here are the answers. Alpha equals 1 for the lasso, and then lambda equals lambda grid, the values that are contained in here. All right, so we fit it, and then what we need to do is to make predictions. So how do we get predictions? Well, we're going to run the predict command, but they set the predict command up a little bit weird in this case. So what we're going to do is to run predict and then convert that into an actual number because the results are by default presented as a matrix for whatever reason. So what do we have to change here? Well, the name of our model is lasso. That's not going to change. The shrinkage parameter that I'm using is this 0.002. So I'm going to go ahead and just copy and paste that into the value of s. Where am I making my predictions? Well, I'm making it on the holdout.lasso data. So I'm going to say new x equals that. All right, so I forgot to delete the .min. Now we're good. Now, when we got these predictions out, we see that we have positive and negative numbers. Because remember, we scaled our y variable, we scaled wins to have a mean of 0, standard deviation of 1. So our predictions are going to be on that scale. We need to unscale those values to basically recover wins in their original units. So how do we do that? Well, if we've saved our predictions to predictions.lasso, we can just run this line as is. Basically what we do is we multiply those predictions by the standard deviation of wins as originally recorded, and then add the average as what was originally recorded. And that gives the effect of unscaling those predictions. I'll look to see what they are now. All right, pretty reasonable. They're not integers, but that's all right. We can get the typical size of the error made on the holdouts by manually calculating the root mean squared error. If I've named all of my variables consistent with what the numerical predictions.r file has, I can run this command as is. I can take a look, and there's my answer. All right, so the lasso, we see, does just a little tiny bit better than if we were to not use it. Applying just a little penalty to the side of the coefficients made the model's predictive performance bump up by just a little bit. Not very impressive, but still. All right, let's try out the other models here. I'm actually going to go and skip ahead to question 7, which is the nearest neighbors. Because it turns out the exact kind of processing that needs to be done for the lasso needs to be done for nearest neighbors as well. So we can pretty much just use the training set, the holdout sample, train.y, etc. that we just constructed. So I'm going to scroll down here and get to nearest neighbors. And I'm just going to copy these lines and paste them into here. All right, so we need to load up the FNN library because that's how we do nearest neighbors regression. And what we're going to do is we're going to make predictions using the command knn.reg. The name of our training data, well, going back to what lasso was, is just train.lasso. This is the data frame of just the predictor variables, scaled to have a mean of 0 and a standard deviation of 1. We're making predictions on the holdout lasso data sets. The predictor variables scaled with a mean of 0, standard deviation of 1. Our answers here is still in train.y, the scaled versions of the number of wins. And in this case, we're going to use a 7 nearest neighbors model, so k is equal to 7. $pred gives us the predictions out. So there's our predictions. Just like with the lasso, we're going to have to unscale those, but same sort of process. We multiply by the standard deviation of the originally recorded values, add in the average of those originally recorded values, and that'll convert that into wins. Not integers, well, some are integers actually, but we can get the root mean squared error on the holdout, the typical size the error made by that model on the holdout sample, by running our line here, and then looking to see, all right, what's it equal to? And it's equal to the anticipated result here. All right, so after you've done the boosted, or sorry, not the boosted tree, the lasso regression, you pretty much get nearest neighbors for free. You don't have to do any extra processing. All right, so back to the vanilla partition model. Well, this is nice because the vanilla partition model can handle, almost any data you just throw at it. You don't have to do anything special with categorical predictors. You don't have to do anything special in terms of scaling. The only thing you really have to worry about is making sure the y variable is nice and symmetric. The x variables can still be skewed. That doesn't really change things. It's all about making sure the y variable looked fine, and it did in this case. All right, so what are we going to do? We're going to predict win from everything on the training data, and we're going to pass the seed of 474 to make sure that everyone gets the same answers. So I think it's actually not pluralized. There we go. What we can see is that, oh, we really only need a simple tree to, do a reasonable job of coming up with a model that generalizes well. So, we're pretty much done here. We need to just figure out what the value of CP is and then build the model and make predictions. All right, so what we're going to do is to find the CP associated with the smallest estimated generalization error, but then only include up to the first 4 digits with no rounding. So this is the smallest value. I'm going to copy that. I'm going to paste that right here, and I'm going to go to 4 digits. So 3, 8, 4, 6. I'm done. I'm going to lop that off, and when I build my model, r part win twiddle dot data equals train, CP is going to be equal to this value. All right, so I'm going to build that tree, and let's get its generalization error. Let's take a look at how well the model generalizes to the holdout sample. So there's my expected generalization error. I see it's a little bit higher than regression, but this was a kind of a simpler model here. Let's actually look at the model itself. This one's small enough that we can see how it's doing its predictions. Basically, it looks at the number of first downs for the season, and if it's small, we head off to the left. If it's big, we head off to the right, bigger or smaller than 284. And depending, we either look at the rushing yards or the number of interceptions. So you'll notice this is a pretty remarkably simple model. There's only 2 things we ever look at: first downs and then rushing yards, or first downs and then interceptions. And basically with 2 rules there, we're able to reproduce a pretty big variety in the anticipated number of wins. It seems to go all the way from about 5 all the way up to about 11 wins, just from those, pretty much 2 simple rules there. So kind of neat, we're able to talk about it here. What seems to be the key to being a winning team? Well, which is the one that has the highest value of y, the highest value of wins? This guy right here. So having more than 284 first downs and having fewer than 12 interceptions. So having at least 284 first downs over the course of the season and having fewer than 12 interceptions. So right is basically answering no to that question. So no, it's not less than 284, so it must be at least 284. No, it's not at least 12, so it must be fewer than 12. All right, so easy to do vanilla partition model. Random forest, way more powerful typically, and still just as easy to do. So to fit that random forest, we always know that we set the random number seed so we can reproduce our results. And we're going to fit the random forest with random forest, win twiddle dot, data equals train, entry equals 1,000 as suggested. We'll run those commands as a pair, and then we can run generalization error on our random forest and see what the error is on the holdout sample. And as expected, it's about 2.4 there. So better than the vanilla partition model, it almost always is. Slightly worse than the regression model. This is one of those few data sets where regression actually does a pretty good job at describing the relationships. They're more or less linear here. But just notice how easy it was to run that random forest. We didn't have to do any sort of variable selection, kind of figure out which variables had to go in. We just threw everything at the random forest and had it figured out. All right, so let me rerun those results. Yep, the answer really was 2.38 here. A little bit better than the random forest. Let's try the vanilla boosted tree here, the GBM algorithm. So typically these models do a little bit better, but it takes a lot more time to actually train them. Usually the time is well worth it, and let's see if it's worth it in this case. So we need to set up train control so that it does the 5-fold cross-validation with 10 repeats. So let's just go to our little cheat sheet here. And to do that, that's going to be this third line here. Train control with repeated cross-validation, 5 folds, and 10 repeats. All right, so I will define that. Now we're going to use expand grid to define GBM grid as a particular set of combinations of parameters. I'm just going to copy and paste this and then modify it as necessary. So we want to consider interaction depth of 1 to 3. Happens to already be there. Entries of 5,000 and 10,000. Okay, let's change this to 5,000 and 10,000. Shrinkage of 0.005 and 0.001. Well, I can just copy and paste that. And we're going to hold n min obs node equal to 10. All right, so we can define our models that we want to be looking at. So it's basically going to consider, it's easy to transpose that m and that b here. It's going to consider 12 different models, varying the interaction depth, the number of trees, and the shrinkage parameter. So let's see what seems to generalize well. All right, so we're going to set the random number seed to 474. Random procedure with repeated k-fold cross-validation. We want to make sure to reproduce these results if necessary. We're going to use the train function to do this, so I'll copy and paste from our numerical predictions cheat sheet. What do I need to change here? Well, I need to make sure that I'm predicting win in this case. The data that I'm going to be predicting from is just going to be the training data here. So I'm saying I can just predict it on the training data. No extra modification is necessary. Method equals GBM. TR control equals fit control, what I defined up here. The metric is the root mean squared error on the holdout. And here are the models that I'm looking at. GBM grid was defined up here. All right, run those two lines as a pair. Give it some time. And once this is completed, we can look what's inside GBM fit to see how well each one of those models was doing, what their estimated generalization error was with that repeated k-fold cross-validation. I'm going to pause this because it may take a while. All right, it is done, so let's look at the results here. So it's gone through each model, and it's given to us what the estimated generalization error is of that model. If we really want to know what the standard deviations were, we can always put $ results here, and it gives us a little bit more detail. And there we go. So there definitely looks to be some difference in performance depending on how we build this boosted tree here. Notice that the overall lowest value of the estimated generalization error was with 5,000 trees, interaction depth of 2, and a shrinkage of 0.01. So 5,000 or 0.001 here. So it is right here. So our lowest was 2.3498. One standard deviation is 0.214. So in theory, anything within one standard deviation of the absolute lowest is acceptable here. So anything below 2.56 would be all right. So this model would be okay, this model wouldn't, etc. All right, so let's go ahead and run a particular boosted tree. What I'm going to have you do shrinkage of 0.001, interaction depth of 2, and trees of 5,000. Just so happens to be those best ones there. I think I need a period right here because that's the way it is specified. And how do we fit this model? Well, let me go back to my little cheat sheet here. Because there is some sort of randomness in the procedure for GBM, I need to make sure to set the random number seed and run these commands as a pair. We're going to be predicting when twiddle dot data equals train, shrinkage of 0.001, interaction depth of 2, n trees of 5,000, and the n min in obs node, we're leaving at 10 here. All right, so run both of these. It's done. Any one particular model is really quite fast. And what we want to do is to find the generalization error. So we need to make predictions. All right, well, I'll just reuse this code from the numerical predictions.r. Predict using the GBM model on the holdout sample. N.trees always needs to match up with the number of trees used to build that model. All right, so we make predictions, and we can get the error on the holdout sample. So holdout $win minus our predictions, sum the square root of those, take the average, find the square root, and we are anticipating a value of 2.31 something. We do not get that, so what? Holdout win. Yep, that's fine. Predictions.gbm. That looks fine. So where did I go wrong? Let me do this both again. Well, I seem to be getting a much smaller number, indicating really quite an amazing model. So I'm wondering if I just had misspecified something when I was going through this. No, I was not. I found the issue where I wasn't actually squaring the error. I was squaring what the average of the difference was between the actual values and the predictions. So let me make sure that that square is in the right place. And now, when I run through my code, I get basically the answer that I was expecting here. A little bit of a difference, not exactly sure why here, but yeah, we're getting a much more reasonable result. All right, so finally, GBM is kind of neat because we can run summary on GBM to get an idea of what the most important predictors were. The larger the number, the larger the relative influence of those predictors. So first downs and interceptions and rushing yards look to be pretty big indicators of the number of wins. And we can even look to see how the model is treating the relationship between wins and any predictor variable by running the plot command, the name of our model, and then the name of our variable that we want to study in quotes. So according to the model, this is what the relationship looks like. Basically, the relationship is pretty flat between predicted wins and first downs up to about 250, and then it increases more or less linearly here, little bends and wiggles, up to about 9 predicted wins at about 350 first downs. Beyond that, there's no additional predicted increase in the number of wins. So kind of interesting. All right, last question deals with the Old Faithful data, basically looking to see, all right, what's the relationship between the waiting time to the next eruption and the last eruption's time in minutes. So let's make a scatter plot of this data. And we see that there may be a linear relationship, but it might be a little bit hard for our eyes to flesh out. All right, so the spline and the lowest models fit a smooth curve. It basically figures out the form of that curve based on the data itself. And it can give us a little bit of insight as to whether or not there are bends and wiggles that might be important. So this code right here tries to fit a smoothing spline with a spar parameter of 0.1. Now remember, this spar parameter is a penalty given to the wiggliness or the curviness of the resulting curve. The larger the number, the smoother and straighter that curve is going to be. So let's just go ahead and fit that with a spar parameter of 0.1, and we can look at the results. Okay, bad spar parameter, bad penalty. We're not penalizing the curviness of this resulting curve enough, so it is just extremely sensitive to any little variation that's going on in the stream of points. So it fits the data pretty well. It has a low bias, but super high variance. This isn't really what the relationship looks like. That model wouldn't generalize well to new data. So let's try this again. Let's see if we can come up with a better spar parameter. What if I increase it to 0.5? That should straighten it out a little bit, make it less wiggly. That still feels a bit too wiggly to me. What about 0.9? Well, that seems nice and smooth. I seem to be pretty happy with that. And what's kind of interesting is that it does point out that maybe there is some sort of nonlinearity going on. It looks like it's rising pretty steeply, where there actually weren't any data points here, but then it tapers off, kind of a small slope, larger slope, and then a smaller slope down here as well. So I would say that the relationship has a little nonlinearity with it. All right, so that's activity 9.